these experiments consist in detecting high-order harmonics of the laser field. So when you expose a gas of atom to an intense laser field, it's possible to generate very high-order harmonics of light. It's very similar to when you play violin and you hit the strings of the violin with a bow, then you generate not only a tone but overtones. It's the same thing but in light. So these high-order harmonics can go from the infrared, where you start from, to the extreme ultraviolet range of the spectrum. And it was conjectured already at the beginning that possibly these high-order harmonics would lead in the time domain to very short light pulses. There has been several steps. First, after these first experiments in 1993, the understanding of the physics behind this phenomenon. And at the same time, also the realization that indeed, in the time domain, we could have very, very short light pulses in the attosecond range. Then, very important, 2001, the demonstration that we had attosecond pulses, both in a series and also single attosecond pulse. A few years later, 2010 maybe, the first experiment where one could really detect electron motion using these attosecond light pulses, and also at the same time the opening towards application in physical chemistry and condensed matter. It's very difficult to predict the future of this field. At the moment, this field is really exploding into many directions. There is, of course, atomic physics and getting closer to quantum information, which I find very exciting. You have molecular chemistry, looking at charge motion at the beginning of a chemical reaction. Condensed matter, looking at charge dynamics, spin dynamics in materials. There are also applications in industry, and the semiconductor industry is interested by this broadband radiation. And there many things happen. You have also progress in laser technology that leads to progress in these sources.